Welcome, dear friends. Am I audible, and whether the whiteboard is seen to you? Please respond in the questions column. Am I audible, and whether you are able to see the whiteboard? Yeah, thank you. Thank you, Tejas. Whether the whiteboard is seen, Tejas? Okay, Tejas. All right, all right. I'm sharing the whiteboard now. Now, whether you are able to see the whiteboard, Vedant, Sushant, Maheshwari. Okay, Yuvraj, thank you. Okay, thank you, thank you, thank you very much. We will be solving one more numerical on entropy change, and this would give you a better insight about what this entropy change tells you. Okay, so you take down the numerical. I'm dictating it, and also I would be writing on the board. Okay, so write down the numerical. 1 kg of water, 1 kg of water at 1 kg of water uh, 1 kg of water at 0 degree centigrade is brought into contact into contact with a source, with a heat reservoir, with a source, that is a heat reservoir, which is at 100 degrees centigrade. Okay, when the water reaches 100 degrees centigrade, estimate or find the entropy change of water, of source and of the universe. Okay, and of the universe. So based on the concepts which we discussed in the last lecture, okay, try to solve this. Okay, I will be discussing with shortly. Okay, so how will you approach this problem? There is water. Okay, it is not ice, mind well, it is water. It is not ice, it's water at 0 degree centigrade, and there is a source. There is a source which is at 100 degree centigrade. So obviously there would be a heat transfer. There would be a heat transfer from the source to the water. So this is after, before, and after means finally what we'll have is the water which is at 100 degree centigrade, okay, in equilibrium with the source which is at 100 degree centigrade. So the heat transfer now stops. Okay, so you need to find the entropy change of water during the heat transfer. You need to find the entropy change of source, entropy change of source during this heat transfer, and you need to find the entropy change of the universe, which would nothing but it would be nothing but the entropy generation because of irreversible heat transfer. Because of irreversible heat transfer. Okay, so calculate this and tell me the answer. So I hope you have copied down the question, and I am now erasing the question. Okay, in order to solve this. Okay, so let me erase this. I hope you have copied down the question. The water which was at 0 degree centigrade is brought in contact with the source which is at 100 degree centigrade. Okay, what happens is the water would be gradually heated. Okay, we are not talking about ice mine well. We are talking about water, and we are talking about only sensible heating of the water. Okay, we are not talking about the phase change also here. So the water is sensibly heated because of its contact with the source, which is at 100 degree centigrade, and as a result of which the water would finally reach a temperature of 100 degrees centigrade. So during this heat transfer phenomena, we are interested in knowing how much has the entropy of the water changed, how much has the entropy of the source changed, and how much is the entropy generation, or what is the entropy change of the universe in this process of heat transfer. Okay, so let me first calculate the entropy change of water. Let me first calculate the entropy change of water. Okay, so before I set up this, I am now to calculate the entropy change of water. Okay, so let me erase this. Yeah, so you see here that the entropy change of water, as we had calculated in earlier problems, is integral of del q by t, and the temperature changes from 0 degree centigrade, which is 0 plus 273 Kelvin, to finally is a temperature of 100 degrees centigrade. So 100 plus 273. So this would be the entropy change of, this is how you will have to calculate the entropy change of water. Because it's sensible heating, so del Q will be mCp dt, because it's sensible heating, mCp dt upon T from 273 to 373. What would happen to the entropy of water, whether it will increase or decrease? Obviously the entropy of water would increase, okay, because heat is transferred to water. So this would be mCp ln T2 by T1, that is 373 by 273. Mass is 1 kg of water. Specific heat of water, you know, it is 4.187 kilojoules per kg Kelvin. This is the specific heat of water. Okay. From this, you will get the entropy change. So tell me the answer for this. Tell me the answer for this. How much is the entropy change of water? Yuvraj, Vedant, Sushant, Tejas, Mohan, Sanket, Gargi, Kevin, Kunal Patil, Darshan, Anamta, Anish, Pritam Roy, Akanksha. Tell me some answer. Anybody has got the answer? So the answer is yes, correct. Tejas has got it. Sushant has got it correct. Tejas has also got it correct. So the answer is plus plus 1.305 or 306, whatever. Okay, plus 1.306 kilojoules per Kelvin. This is the entropy change of water, right? Now find the entropy change of the source. Now entropy change of the source would be integral of del Q by T, and you know the concept of source. Source is a reservoir whose temperature remains constant. So I can take the temperature outside the integral. So this is nothing but Q upon T. And I will put a negative sign over here. Negative because the heat is lost by the source, and hence the entropy of the source is going to decrease. So entropy would decrease because the heat is lost. Okay. So hence I am putting a negative sign. So I am putting a negative sign over here. So it is minus Q upon T. Okay. So calculate that. For that you need to calculate the heat transfer. So how will you calculate the heat transfer? The heat lost by the source. Heat lost by the source. How will you calculate that? How will you calculate the heat lost by the source? This Q. How will you calculate this? Anybody has the answer? How you calculate this? Heat lost by the source. Heat lost by the source. Yeah, correct. Sushant, it's correct. Heat lost by the source is the not heat gained by surrounding. Heat lost by the source is the heat gained by the water is equal to the heat gained by water. Okay, heat lost by source is heat gained by water. Heat gained by water is mass of water, specific heat of water, and temperature difference of water. So temperature difference is 100 minus 0. 100 minus 0. Mass of water is how much? Mass of water is 1. Mass of water is 1 kg. Specific heat of water, you know, it is 4.187. So 1 into 4.187 into 100. So the heat transfer value, this Q value, by calculating it as MCP delta T, MCP delta T comes as 418.7 kilojoules. So once you get this value as 418.7, you calculate now the entropy change of the source. Calculate the entropy change of the source now and tell me the value. It would obviously be negative. Entropy change of the source would be negative. So tell me the value of entropy change of the source, that is the reservoir. Entropy change of the reservoir is what? Entropy change by the reservoir is what? Anybody has the answer? So you need to be clear that this T is the temperature of the source, okay, which is obviously 373 Kelvin. So 373 Kelvin. So minus 418.7 upon 373. So that comes as minus 1.122. Check this answer. So are you getting this? Are you getting this value? Okay, correct. Yugandhara, you are correct. It is minus 1.122 unit is kilojoules per Kelvin. Kilojoules per Kelvin. Now you find the entropy change of the universe. You find the entropy change of the universe. That is the entropy generation during this heat transfer process. Find the entropy generation during the heat transfer process. That is the entropy change of the universe. How will you find that? So it's simply a summation of entropy change of water and entropy change of source. Okay, and you will see that you will get a positive value. You will get a positive value, which means that the entropy generated in the universe. And why is that generated? It has generated because of irreversible heat transfer. It has generated because of irreversible heat transfer. Okay. So what is the value you are getting now? Entropy change of the universe. So entropy change. So let me erase this now. Let me erase this. So the entropy change of the universe is the entropy change of the source plus entropy change of the water. Entropy change of the source plus entropy change of the water. Okay. So entropy change of the universe is equal to entropy change of the source plus entropy change of the water. And what was the entropy change of the source? The entropy change of the source is minus 1.122, and the entropy change of water is how much? 1.306, which comes as approximately 0.183 kilojoules per Kelvin, which is the quantification of because of irreversible heat transfer. Because of irreversible heat transfer. Okay. Now the interesting part would follow. This is okay. You had already known this calculations. Now that is not very interesting. Now we would be trying to reduce. Okay, we would be trying to reduce the irreversibilities. Okay. How we will be reducing these irreversibilities? Let us see. Okay. So now again we would consider the part 2 of the problem. Our aim is the same. What is our aim? Our aim is to heat the water from 0 degree centigrade to 100 degree centigrade, right? But now what I'm going to do, before that, let me ask you whether you have copied down this thing, this first part of the numerical is clear to you, and you have copied down this numerical, the solution of it, yes or no? Before I proceed, I want you to confirm that you have copied down this numerical and you have understood this first part. Please let me know that whether you have really followed this. Okay, I'm not getting your responses, maybe because of network issues, but I will assume that you have followed the first part of the numerical. Okay, somebody can put it in the chat box. Chat box, you can put your message saying that you have followed and it is copied. Someone of you, and you put something in the chat box. Okay, whatever. So let me move to the next part of the question. I'm erasing this now. I'm erasing this now, and I am considering a very interesting kind of stuff wherein my attempt would be to reduce this irreversibility. Okay, my attempt is now to reduce this irreversibility. So how I plan to do now is, so my aim was to heat the water. Heat the I want to what I want to do is that there is water which is at 0 degrees centigrade, and I want to heat it to water at 100 degrees centigrade. And for that, what I did was, earlier I brought it in contact with the source. Okay. Now, case 2, what I will be doing is that I will take this water which is at 0 degrees centigrade and bring it in contact with the source, which will be at, let us say, 50 degrees centigrade. Okay, so what will happen is that in this step 1, what we'll get is that you'll get the water now. Water would heat up to 50 degrees centigrade. Okay. Then in step 2, what I will do is that I will take this water which is at 50 degrees centigrade. Okay, and I'll bring it in contact with the source now, but now the source is at 100 degrees centigrade. Source is now at 100 degree centigrade. Okay, so instead of what was case 1? Case 1 was that you brought the water in contact with the source at 100 degrees centigrade. So case 1 was a one step heat addition, okay, where the maximum delta T was 100 degrees centigrade, delta T between source and water was 100 degrees centigrade. In step 2, what I am doing is that I am reducing this delta T between source and water to one of the original delta T. So this delta T now is 50 degrees centigrade. It means that there is some delta T between the source and water, but that delta T is now significantly smaller. Okay, it is now 50 degrees centigrade. Now what happens to the, because of this two-step heat addition process, the heat addition quantity remains the same, which you would now calculate and convince yourself, but you would find that the entropy change of the universe has decreased. Okay, you calculate this now, you calculate the entropy change in case 2. Calculate entropy change of source, calculate entropy change of water, and calculate the entropy change, that is the entropy generation, entropy change of universe, that is the entropy generation. So the entropy change of source and entropy change of reservoir you need to now find out. Okay, so what would be the entropy change of water? The entropy change of water and entropy change of source. So entropy change of source would be delta S of source 1 plus delta S of source 2. So delta S, this is source 1, this is source 2. Okay, delta S of source 1 and delta S of source 2. What is delta S of source 1? Delta S of source 1 would be Q1 by T, right? And this is minus. Okay, so what is this T in this source 1 T? Source 1 T is 50 plus 273. 50 plus 273. And what is Q1? Q1 is mass into specific heat to delta T, means 1 into 4.187 into 50 minus 0. So Q1 is 1 into 4.187 into 50 minus 0. And what is T? T is 50 plus 273. That is the temperature of the source 1. Temperature of the source 1. So this if you calculate, you will get, this will get the value as minus 0.647 kilojoules per Kelvin. Similarly, the value of entropy change of source 2 would be minus Q2, let me call this as source 1 temperature, upon the temperature of source 2. So what is Q2? Q2 will be minus of 1 into 4.187 into 100 minus 50. Okay, the temperature of the water changes from 50 degrees centigrade to 100 degrees centigrade. Okay, upon T. What is the T here? So T here is now 100 degrees centigrade. So 100 plus 273. So this, if you solve, you should get it as minus 0.56 kilojoules per Kelvin. Okay, and the addition of this two, you tell me the addition, do the addition and tell me the entropy change of the source. Do the addition and tell me the entropy change of the source here. What is the value you are getting here? Entropy change of the source. Yuvraj, Yugandhara, anybody? Tejas, Vedant, Sushant, Shubham Hande, Sanket Jadhav, Mohan, Neha Aire, Maheshwari. Anybody you can tell me the answer? So the answer is the entropy change. The entropy change of the source is, it is 0.647 plus 0.56. Okay, so you need to calculate and see for yourself. Then entropy change of water. What would be entropy change of water? Entropy change of water would be the same. Okay, and how it would be same? You can convince yourselves by calculating that. Entropy change of water would be the same, but how to calculate that? It would be again delta S of water 1 plus delta S of water 2. Okay, now delta S of water 1 is what? Let me write down here. This delta S of water 1 means your first step of the case 2. First step of the case 2. So this, when you are heating the water from 0 degree centigrade to 50 degree centigrade, that delta S of water 1 is integral of Cp dt upon T from 0, that is 0 plus 273, to 50 plus 273, and delta S of water in the second step, step 2, when you are heating the water from 50 degree centigrade up to 100 degree centigrade, would be 50 plus 273 mcp dt by T. Okay, so if you add these two, delta S1 and delta S2, okay, you can solve this and you will find that you will get the same value, that is 1.305 kilojoules per Kelvin. Kilojoules per Kelvin. And then if you do the, let me use some another pen now. Case 2, entropy change of the universe is delta S of source 1, source, plus delta S of source second, plus the entropy change of water, which is 1.305, entropy change of water. Okay, in addition of the two, that is W. This is actually delta S W1 plus delta S W2. Okay, so all this if you put the values here, this is minus 0.647 and this is minus 0.56. Okay, and this is 1.305. What you'll get is, you will get the value as minus 0.098 joules per Kelvin. Okay, I hope that you have got this calculation. Now what is important is not this value, how you get the value. You should calculate this and convince yourself that you will get this number. But numbers are not important. What I want to tell you is a more interesting part, which would be followed by these numbers. Okay, so whether your calculations are correct, you understood these calculations? Yes or no? Tell me whether you have followed this. Okay, Yugandhara. Yuvraj, have you followed this? Okay. I'm not sure. Maybe that these questions have a limit of responses. So it could be that all the responses are now already full. Okay, the question box might be full. That could be the reason why I'm not getting your answers. Okay, whatever. So assuming that using a blind approach, I'm assuming that you have understood the steps. Okay, now let me look. I will now explain this problem from a conceptual angle. Okay, so I'll be erasing the entire thing and I would be explaining you the problem from a conceptual perspective. Okay, so let me erase this. Let me erase this entire thing. So I'm clearing the canvas, and now let me discuss the conceptual feature of this problem. So what was the problem? The problem was, there is a water which is at 0 degree centigrade, and this water was to be heated up to 100 degrees centigrade. Heated up to 100 degrees centigrade. So in the case 1, scenario 1 of the problem, what was done, that this heating was done irreversibly from by bringing the source in contact with the water, and this source was at 100 degrees centigrade. So this delta T between the source, that is source temperature, and the water temperature was initially 100 degrees centigrade. Okay, and gradually it decreased, obviously, right? So this, because of this finite temperature difference, which is considerable, which is 100 degrees centigrade, we already know that this heat transfer phenomena is an irreversible heat transfer phenomena. Okay, so when we calculated, and this we quantified by calculating the entropy change of the universe, that is the entropy generated. So entropy change of the universe you got in the case 1 as 0.183 kilojoules per Kelvin. Okay, so this, the meaning of this value being 0.183, which is positive value, the meaning is that this process is irreversible. This process is irreversible. And as I had explained in the yesterday's lecture, if we reduce this, okay, if we reduce this value, then the irreversibility is reduced. Then the irreversibility is reduced. Okay. So how did we reduce the irreversibility? So what we did was, in the case 2, in order to reduce the irreversibility, I planned the heat addition in 2 steps. Okay. So what I did was that I maintained the temperature difference. Instead of 100 degrees centigrade, I maintained the temperature difference as 50 degrees centigrade. So first I brought the water in contact with the source, which is at 50 degrees centigrade, and then this was a step 1, and in the step 2 I brought, so this water was 0 degrees centigrade, it became finally, it came to, it heated up to 50 degrees centigrade, to 50 degrees centigrade, not more than that, because the source is at 50 degrees centigrade. Then in the step 2, what you did was, you took this water which was now heated up to 50 degrees centigrade, okay, and you brought this water in contact with the source. The source is now at 100 degrees centigrade. Okay, so now again there was a heat transfer. And gradually this water now attained 100 degrees centigrade. So that was our objective finally. What is the objective? Objective is to heat the water up to 100 degrees centigrade. So in the case 1 also we had achieved this. Case 2 also we have achieved this. And in both the cases, please note, in both the cases the heat transfer is the same. In both the cases, the value of the heat transfer would be the same. Okay, if you calculate in both the cases, you will find that the total heat transfer, that is, in this case, the heat transfer was 418.7 kilojoules. In this case also, this is Q1 and this is Q2. So in this case also, you find that the heat transfer remains the same. That is Q1 plus Q2 remains the same, that is 418.7. What changes? Then what changes is the irreversibility changes. Okay, with the delta T changes, right? So if you see our calculations, so you'll find that the entropy change of the universe in the case 2. Okay, so initially it was 0.18, and in the case 2 you have got the value as 0.09. Okay, 0.98, right? So you look at these values. If you compare the value of entropy change in the case 1 and case 2, what you would find is that this entropy change of the universe has now been reduced. And why has this reduced? This has been reduced because irreversibility has been reduced. Okay, so you find that the irreversible heat transfer has been reduced in the case 2. Okay, so we are now progressing towards reversibility. So the irreversible heat transfer is reduced. And why is this irreversibility reduced? This is because the finite temperature difference has been reduced between the source and the water. If you do a thought exercise wherein you have the water which is at 0 degrees centigrade, you bring this water in contact with now source which is at 10 degrees centigrade, then the water would reach to 10. This water which is at 10 now, bring in contact with the source which is at 20 degrees centigrade, the water would get 20, so on and so forth, Ultimately, you would be getting the water at, let us say, 90 degrees centigrade, bring in contact with the source which is at 100 degrees centigrade. You will find that by the case 3 also the heat transfer remains the same, but the entropy change of the universe would be negligibly small. Okay, so what it means is that if you do the heat transfer in a manner such that the difference between the source temperature and that of the fluid which is taking that heat, if that difference is reduced gradually, okay, if difference is reduced, then or the finite temperature difference is reduced, it means that the irreversibility is reduced. And the beauty of the concept of entropy is that we can now quantify what is the irreversibility, and you can show by numbers that the irreversible heat transfer has been reduced, and this the proof is that the delta S of universe, you will get the value as considerably smaller. Okay, in an idealized case, when there is no temperature difference, there is negligibly small temperature difference between the water and the source, right? Every time you heat that water, you will find that the delta S of the universe is 0, and then you can say that the heat transfer phenomena is reversible. I hope you have understood this concept well. Okay, so I want your responses if you understood this, or you want me to repeat this. I will, because maybe I'm getting the responses, I would make 1 or 2 as a panelist, and that would help me in getting your feedbacks. Let me try making Yugandhara as a panelist. Yugandhara, I made panelist. I'm trying to make Yuvraj as a panelist. And maybe Yugandhara and Yuvraj, can you now speak? Tejas, maybe Tejas I can make as a panelist. Tejas Anab. If you are now able to communicate with me, and the people whom I have made panelist, you can communicate with me. If you have a laptop, maybe, or I don't know. Let me try somebody else also. Can you speak from your side? Anamta, let me try Anamta also. I'm making her a panelist. Anamta. Then you can see some numbers, whatever. Kunal Ranade. I'm making Kunal as a panelist. So there are so many panelists now. Can anybody speak from your side? Can you communicate from your side and tell me whether you have followed this concept or no? Kunal, Tejas, Sugandhara, Yuvraj, Anamta. None of you can communicate? Okay, let me unmute you. See, I am unmuted all of you. If you are able to communicate from your side, you just tell me whether that is. I unmuted all of you. You can unmute from your side, and if you have that facility, you can communicate with me and explain me whether you are really followed the concept. Gargi, Sushant Kanade. All right. Ganesh Shikare. Tejas is saying he has understood, but yeah, Sushant is saying he has understood. Sanket is also saying he has understood. So hopefully, okay, hopefully you understood the concept. And in the next class, I would be using the concepts which are shared with you in the form of videos. Yesterday I shared with you 2 videos prepared by Professor Murukar. So in the next class, we will be solving the concepts. We will be solving numericals based on those concepts, right? So I want you to please spend some time at home, because it is important for you to spend some time. Okay, without which it would be difficult for you to comprehend. So please spend some time at home, watch the videos, okay, and come back prepared for the next class, right? So have a good day. Tomorrow is holiday, so enjoy that holiday, and come afresh in the next lecture of us. Okay, so thanks for joining. I don't want you burden with you. I don't want to burden you with one more problem. Okay, these problems are just a feature. Let me tell you, the problems are not very difficult. Okay, in terms of solving it, what you need to appreciate is the concept, right? Putting the values and solving it is not a big deal in this kind of problems. You need to appreciate what is happening there, and then you need to use the correct expression for that. That is only the trick in this kind of problems. So all the entropy change problems are very simple to solve, okay, mathematically speaking, but conceptually speaking, you need to understand, and also without understanding also you can solve it by remembering the formulas, but then that won't make you really enjoy those concepts. Okay, so if you want to really enjoy those concepts, and if you want to really appreciate what is happening physically, okay, and what that numbers are telling you, then you must look at it from the conceptual angle. Okay, so thank you very much. Bye for now.